An inactive replication slot silently pinned 180 GB of WAL, filling the primary disk in 72 hours. Writes crashed with no space left on device. Here's exactly why. Welcome to TheCodeForge. Before we dig into that production issue, let's cover database replication. Database replication copies data from a primary to replicas to distribute read-load and provide failover. The primary handles all writes, while replicas serve reads. This architecture is simple and conflict-free. Primary replica is the default. One writer, many readers, zero conflicts. Multi-primary allows writes on any node, but introduces conflict resolution complexity. Use primary replica unless you genuinely need horizontal write scaling. Run these queries on the primary to see connected replicas and their lag in bytes. On a replica, confirm it's in recovery and check the time-based lag. When multiple nodes accept writes, conflicts happen. LWW uses timestamps and silently discards the loser. Vector clocks detect true conflicts and require application resolution. CRDTs are mathematical structures that always converge but only work for specific data types. This Python class simulates a vector clock. The dominates method checks if one clock is strictly newer. If neither dominates, the clocks are concurrent and a conflict exists. Asynchronous replication confirms the write to the client immediately, risking data loss if the primary crashes before shipping WAL. Synchronous replication waits for a replica acknowledgement, guaranteeing durability but adding network latency. This Docker Compose file sets up a primary and a replica. The replica uses PG base backup to initialize from the primary and then start streaming WAL. Replication lag is the delay between a commit on the primary and visibility on the replica. Time-based lag tells you user impact. Byte-based lag tells you how much WAL is queued. Monitor both. Run the time-based query on the replica to see how stale the data is. Run the byte-based query on the primary to see the WAL backlog. Alert on both with separate thresholds. WAL is the foundation of replication. Every change is logged before touching data files. Replication slots guarantee WAL is retained until the replica consumes it, but an inactive slot can pin WAL indefinitely, filling the disk. Check your WAL level and replication slots. The query highlights inactive slots retaining more than 1 GB of WAL, a critical alert condition. Automated failover tools like Patroni detect primary failure, promote the best replica, and update the connection endpoint. Fencing ensures the old primary stops accepting writes to avoid split brain. This Patroni configuration sets up a cluster with its settered for leader election. The maximum lag on failover ensures only a nearly caught-up replica is promoted. Star topology is the default. All replicas connect directly to the primary. Cascading reduces WAL shipping load on the primary by having Tier 1 replicas serve Tier 2. Multi-region places replicas near users for low latency reads. These comments illustrate the 3 common topologies. Star is simplest, cascading helps at scale, multi-region improves read latency globally. This is the same issue we highlighted at the start. Here's exactly why that happened. A replica fell behind due to a slow query and disconnected. But its replication slot remained active, telling the primary to keep all WAL until that slot consumed it. Without max slot WAL keep size, the WAL grew to 180 GB, filling the disk and crashing the primary. The fix was to set max slot WAL keep size to 10 GB, capping how much WAL any single slot can pin. Additionally, drop inactive slots before extended maintenance and monitor slot retention. This prevents a single dead replica from taking down the primary. Without a cap on WAL retention per slot, a single inactive slot can pin WAL until the disk is full. Always set max slot while keep size to a reasonable limit. This is the exact line that caused the incident. Without a cap, an inactive slot can pin WAL indefinitely. Always set max slot while keep size to a reasonable value like 10 GB. Synchronous replication adds network round-trip time to every write. Always benchmark under production-like load before enabling it, or you may be surprised by the latency impact. If the old primary is still running during a network partition, promoting a new primary without fencing creates two nodes accepting writes. Always include fencing in your failover sequence. In PostgreSQL 15, the max slot WAL keep size parameter was introduced to cap WAL retention per replication slot. Prior versions relied solely on WAL keep size, which could still allow unbounded growth if a slot was inactive. The article recommends setting max slot WAL keep size. This is critical for PostgreSQL 15+ and should be set to prevent slot bloat from filling the primary disk. The article warns about inactive replication slots retaining WAL. Here's a concrete query to identify slots that are inactive and retaining significant WAL, and a command to drop them after confirming they are no longer needed. The article states replication is not backup, but doesn't elaborate. A destructive DDL, e.g., drop table, propagates instantly to all replicas, and replication cannot recover the data. Always maintain independent backups, e.g., PG dump or WAL archiving, with a retention policy separate from replication slots. To complement replication, enable WAL archiving so you can perform point-in-time recovery, PITR, independently of replicas. This snippet shows the required PostgreSQL conf settings for archiving to a local directory. To diagnose slot bloat, query PG replication slots for inactive slots with large retained WAL. Monitor lag with PG stat replication. Set alerts on both metrics. Let's run through some common interview questions. What is replication lag and how do you measure it? Time-based and byte-based. Query PG stat replication and PG last exact replay timestamp. Explain the difference between synchronous and asynchronous replication. Sync waits for replica ACK, async does not. Sync has zero data loss but higher latency. How does a replication slot cause primary disk bloat? An inactive slot pins WAL until consumed. Without max slot WAL keep size, it can fill the disk. And a few frequently asked questions. Is replication the same as backup? No, destructive DDL propagates instantly, always maintain independent backups. Can I use async replication for financial transactions? Not recommended. Async risks data loss on primary failure. What is the default replication topology? Star topology, one primary with multiple direct replicas. To sum up, replication is for red scaling and failover, but introduces failure modes like slot bloat. Always monitor lag, cap WAL retention, automate failover with fencing, and give replicas enough I/O capacity. Ready to go deeper? Up next, database sharding, then database indexing, then normalization versus denormalization. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.